This week we're covering two topics, one of which is binary outcomes in hierarchical models. So this video is going to be about hierarchical generalized linear models. If you're a bit confused still about what logistic regression is or what generalized linear models are, I suggest you take a look at the optional video for this week and the optional material. I go into some more detail about single level logistic regression in that video and provide some of the intuition. In this video, we're going to assume that that is more well understood because that will likely be more review for some of you, while some of you may want a little bit more background on it. So everything that we've said so far about HLM can also be applied to logistic regression, more or less. The key difference is that we don't have the epsilon error term, or the residual, so we don't have a sigma squared epsilon either, or the variance of the residual. The reason is that in normal regression, our model provides a direct estimate of our response, and we denote this y hat. And we get residuals by subtracting y hat from our actual observed y. And this is where we get the epsilon from. In logistic regression, we're not actually estimating our response variable, we're estimating the probability of our response variable. And that's because our response variable is on the 0, 1 unit. And when we estimate the probability, this is already a representation of how much our model estimation is deviating from the actual observed value. So adding the residual would be redundant. What we do still have are random effects. So for example, we have our random intercepts, sigma squared mu 0j, and this represents the cluster variance in the intercept, which in this case is the estimated log odds of the outcome when any of the predictors are 0. In single level regression, it's the estimated mean. In generalized logistic models, it is the estimated log odds of the outcome instead of the intercept. So this data is an extension of the growth curve modeling we looked at previously. In this example, we estimate whether a depression diagnosis was categorized as severe or not in repeated observations over time while participants were in treatment. The relevant data file is depressed cat, and the variables that we'll be focusing on are severe, which is the outcome variable, and weak, which is the time variable, and the person variable being ID. Note that weak is already centered at week 1, so we don't need to mess around with centering it. But if it wasn't, remember all that centering stuff we talked about in growth curve models, where you have to pick the reference time point. And we can extend the Elmer function in LME4 by adding a g on the front and calling glimmer. And so this is the generalized linear mixed effects regression, is what that stands for. And the only extra piece in addition to that is that you now have to specify the family of link functions and then the link function itself. So here we're specifying family equals binomial and link equals logit. You can also specify link equals probit for a probit model, but logit is far more common and far more interpretable, so we're going to focus on that. So first, we can talk about interclass correlation. So because we don't have sigma squared epsilon, a common procedure is to simply replace it with a constant, pi squared divided by 3. And so this is what we're going to do here. So you note that when we fit our model, we use the glimmer, GLMER, and we here fit an unconditional model where we have severe predicted by the random intercepts or the estimated cluster log odds. So remember, this is not cluster means, it's cluster log odds. And so then we specify family equals binomial, link equals logit, and that tells Glimmer that that's what we're doing. We're looking at the cluster specific log odds rather than the cluster means. And we get our output, and you see our random effects. In our random effects table, we only have one row now. We don't have two rows because we only have sigma squared mu 0j, no sigma squared e. And so we plug in our sigma squared mu 0j into our ICC function, and we divide it by we divide sigma squared mu 0j by sigma squared mu 0j plus pi squared divided by 3, which again is a constant. It's constant. It's about 3.289, and we get 0.287 for our ICC. And note that in the performance package, the ICC that you get is also following this formulation for a logistic model. So here the interclass correlation is the same if you call the performance ICC function. So we can visualize the growth curve model, and I'm sorry my code's a little cut off here. I'll fix that in the lecture slides. But either way, we can visualize the growth curve similar to how we did before when we did it to try to tell if the relationship was linear or nonlinear by looking at uh, the average values at each time point. The issue here is that we have to remember that these are now proportions of severe diagnosis at each time point, and this means we don't necessarily expect this to either be linear or curved to determine how we specify our model. We actually expect this to be curved. We expect it to either be the S sigmoid shape or the reverse S sigmoid shape or a segment of an S sigmoid shape because our model is already nonlinear by virtue of us doing a logistic model rather than a standard linear model. So the best way to really check for extra additional nonlinear relationships, like if you need to include exponential terms or a piecewise model, is to test those if you have some intuition that they might be the case, and just use likelihood ratio tests to try those out. But for the most part, we can just use standard logistic regression with linear terms. So here's what we see. We see this growth curve model. It is very much not a straight line, but this again is to be expected. We see it decreases not very sharply at first, then it decreases very sharply in the middle, and then it decreases less sharply at the end. This is very similar to a reverse S shape or a reverse sigmoid is what this looks like to me. So I have no reason to suspect this is not just a standard logistic link. One thing that's not as useful is the spaghetti plot. So because there are no cluster-specific slopes necessarily, we really can't visualize empirically the spaghetti plot very well. It just kind of looks like a mess. And my advice is just generally try random slopes if you have enough observations per cluster, and as long as the model converges. If you have lots of issues or you don't have enough observations per cluster, or you're getting convergence issues, try it without them. For the most part, you're not risking too much overfit by including them, but you are risking more underfit by not including them. And so here's the output. Here are the fixed effects. So remember, these fixed effects are log odds. So we can get them into odds by taking the exponent. So here the log odds for week is minus 2.06. So if I take the exponent, that means the odds for week are 0.127 and or 0.13. So put another way, well, what this means is that the odds of severe diagnosis decrease by 0.13 for each week that passes. Another way to think of this is that the probability of a severe diagnosis is 13% as likely as the previous week for each week that passes. So that's the sort of straightforward, intuitive, interpretable way of looking at these coefficients. We can also look at the random effects. There's nothing really special here. The only difference is that these are variances in log odds rather than variances in means, but otherwise everything's the same. So one issue is with significance testing, and that is that there is no known degrees of freedom adjustment for logistic regression in the same way there is for linear hierarchical models. So the sort of most straightforward method is to do likelihood ratio tests. And so we can do those for each parameter. So if we have multiple predictors and we want to test the significance of each predictor, we could do repeated likelihood ratio tests. This could get really tedious the way we've learned so far. So there's actually a package called AFEX that provides the mixed function. And this will allow you to what this essentially does is it keeps refitting different models, deleting one predictor at a time, and then running likelihood ratio tests, and then it outputs a table with each likelihood ratio test. An alternative is to do parametric bootstrapping, but just a warning, both of these methods are extremely slow, especially parametric bootstrapping. It could take really, really long time. And as a second warning, if you have a complex model, don't be surprised if you get convergence failures when trying this. And again, this is even more true for parametric bootstrapping because parametric bootstrapping keeps refitting the model on different samples of the data, and in some proportion of them, the convergence is going to fail, and there's not too much you can do about it. And if too high a proportion of the bootstraps fail, you can't really trust your results. It'll still give you results, but you can't really trust them. So the likelihood ratio test is a little bit more stable and generally preferred, but you could still run into convergence issues when it starts refitting the reduced models for the likelihood ratio test output. But either way, the parametric bootstrap, even for this model, is taking a fairly long time, so I just didn't do it. Instead, here's the output for the likelihood ratio test, and what you can see what this does is it fits 3 different models. It goes one at a time. It starts with the full model, then it deletes one variable, and then it deletes the other variable, and then it does 2 different likelihood ratio tests comparing the full model to each reduced model, and that's how you get your p-values. And keep in mind, because I specified a random slope for week, it keeps the random slope for week in each term. So it's not, these are degrees of 1 degree of freedom tests, where they're essentially testing the null hypothesis that the parameter for week here would be 0, even though there are variable slopes. The slopes vary by person, but so that this is testing is that the average slope is 0, the fixed effect is 0. And finally, we can visualize our results using the ggfx package. And so we've looked at this several times before, and what we see here is that we don't quite get the full predicted S shape out of these results, but we do get a curve. We get sort of an elbow here. So we're getting a lot of observations that are up here close to 1, and then decreasing over time. Presumably this levels off because remember this is logistic model, so it can never estimate values below 0. And notice that the confidence bands do the same thing, so the confidence bands are limited at 1 and 0.